Yeah, my screen is visible.
Yes,
Uh,
visible, and you are loud and clear.
Fine, sir.
Okay.
So just want to interact with some of the participants. By now, just one small question I'll put, and if anybody can answer me, that uh, why the ionospheric delay is important. Any answer for that? Anybody from the audience? Maybe they are in listening mode only.
Oh, please, somebody please answer, because you were hearing for a long time.
Yeah, 1 hour I have spoken.
Yes.
Or otherwise, how we estimate the ionospheric delay? What is the basic method or basic concept? Anybody from audience? Anyone?
Please try to answer. Whatsoever may be your answer, please try to answer.
Sir, as you told that, and as we know that the ionosphere density is changing with time, that is the ionospheric error which occurs, that is not constant throughout the day or throughout we can call a particular time. It is important to estimate the ionospheric delay as it creates some variable errors in our calculation method. If it is a constant value, then we can find some method, and we can eliminate it from our calculation, and we can get an accurate measurement. But if it is changing with time, as the total electron concentration is changing, as you said that, so I think that for that reason ionospheric delay count is more important.
Yeah. Very nice and very good answer. And the concept which actually behind the estimation is like we have to take differential delay between two frequencies, any two frequencies from the same constellation, from the same satellite. So if we are assuming the NavIC satellite, then the satellite number, then you get the L5 and S band, then the total range delay. That delay, if you differentiate, then you get the TEC, which is the columnar integrated, this columnar, the column which you can see here, columnar integrated electron content, which is called total electron content, TEC. And it is measured in terms of the electrons per square meter. The square meter is actually understanding that the total number of electron in a cylinder of 1 meter square cross section. So the assumption is simple, theoretical assumption, that along the line of sight there is a 1 meter square cross section cylinder in which how many electrons are there, that is the total count. So this actually is normalized with 10 to the power 16 electron, and then it is given as 1 TEC unit. So this one must remember for GPS and all GNSS. In modernized system, the TEC is 10 to the power 16 electron per square meter. Now, when we talk about 10 TEC, 15 TEC, that is the multiplication of this particular number, which is a normalized number of the number
Sir,
of electrons.
sir, I have one more question, sir. In this particular slide, that
Uh,
sir, we know that when from the concept of light, sir, when the reflection occur in a medium,
hmm.
then there is a bending of light. That you can say that in this slide, that causes slant delay.
Yeah.
Sir, but you also said that we have to count the vertical delay also. But sir, if the ionosphere is, we can think that it is like behave like a cell. So sir, there must be the slant delay. So why, sir, we can count the vertical delay that is not actually happening? Sir, actually this is a layer,
Yeah.
and the and the signal is go through it, and it only suffer the slant delay, I think that. But
Yes. Yes.
you can say that vertical delay count is
Yes.
also important, sir. Why can this?
Yeah. So the answer is two different parts. The part one is I already told you that there is a assumption of single layer. When you assume a single layer around the Earth surface, now Earth is a curved surface, and if you want to put the map of the ionosphere, then this ionospheric single layer assumption becomes very important and significant. So assume that another layer on the Earth at around 350 kilometer covering the whole Earth is there. Now, like you straighten or stratify the spherical Earth into one particular square map. Similar way, we can develop ionospheric map. Now that becomes a two-dimensional map of the ionospheric TEC. Now the trouble is that in this kind of mapping, we do not have any particular relevance for slant delay because it is a point. You understand that? So for a person who is standing here on the Earth below the error, it is that point on his head which is actually referred for that map. So all the models, when they transmit the corrections from satellite, or like you tell a user that this is the overhead delay, then you tell only overhead in terms of what is vertical cylinder. But what you said is actually correct, that the delays which are happening in the GPS satellite are slant. So now the issue comes that how to convert slant to vertical and vertical to slant, because nobody knows at one particular moment the user which is here, who is having receiver, is having a satellite in what direction. So what particular elevation or azimuth I should give to have that kind of slant model. So we cannot have slant model for all the directions, but we can have one model which is in the vertical direction, then we can convert into. So that is like mathematical simplification of a very complex problem. However, when we do these conversions, there are definitely errors involved, and those errors actually finally account for our accuracy in the position. So the vertical delay is like a map all over the Earth, and then since vertical delay can be transmitted easily as a message, also it can be considered as an overhead delay. That's why vertical delay is mostly popular in the community. However, slant delay is the real delay. So they again convert. So this is a issue which we have not been able to resolve. However, there are solutions which come up with multiple layers, like not single layer. We consider 2 layers or 3 layers, which are most important. And then we give those delays as 3 different maps. Then we try to fit a mathematical function and get the real delay which is happening in the slant. So it will be better or more accurate. But then these are like part of the research, and right now operational method only vertical delay is used. So that is the whole understanding about vertical and slant delay. Am I clear?
Yes, sir. Yes, sir.
Okay. So shall I will proceed now. So these applications I will not talk because you will hear a lot of them. But what the important left side column I have shown is these applications actually, they are actually providing an opportunity for atmospheric research, because people who want to get the position, they invest in the receivers, they invest in the geodesy, then they provide us the data. That data becomes an opportunity for ionospheric research. So actually GNSS and NavIC signal or whatsoever satellite navigation signal, they are not made for ionospheric research purpose, but since these signals provide an opportunity, it has become a very, very valuable global resource. So this resource actually is useful for our research purpose, or for again giving a feedback to accurately provide the users their position and all. And there are several users in industry, sport, transport, science, several type of users which require this application. And we use this kind of receiver. So for the purpose of ionosphere, we require dual frequency receiver, which are actually costlier affair than your single frequency receiver. There are some low cost solutions available for dual frequency, but then we don't get the accuracy. So there is a trade-off between the accurate position, accurate range information, or accurate phase and code measurements versus the price. So you pay less price, you get lesser accuracy in the range measurement. Once your range is not accurate or they are noisy, then your TEC or the water vapor becomes highly noisy. So it is a direct relation of the how much kind of commercial market in which the precise solutions are available at different companies and different brands are there. I have just given some these brands like Novatel, Java, or Septentra, Trimble, but then there are n number of companies, and definitely you will get lot of information in due course of your workshop. These ultimately, actually, when we come to the what we actually get from the receiver, so we get this kind of data files for the purpose of atmosphere and atmospheric research, even for the purpose of precise positioning, even for the purpose of navigation, your position finding. So these files are actually internal generation data, or the raw data, what is called from the receivers. Either it is a single frequency or a dual frequency receiver, they always generate these kind of observation and navigation files internally in binary format, externally in the human readable format. So what we are seeing is ASCII format, and this format, left side is known as observation file. It provides us a kind of types of different observation like C by A code, C by A code, C by A code in different 1, 2, and 3 frequency, then P code, which are the ranges. So now there are total 14 different kind of observations available on that particular day, on that station. Okay. And then this is the day of observation, 15 March 2015. This is start of observation, end of observation. How to read? So for a given moment like this 15th March 2015, 0 UT, 0 hour, 0 minute, 0 second, there were 17 satellites available on that particular site, with G means GPS, so many satellite, R means the GLONASS or Russian number of satellites, and each satellite will have these 14 observations available. So G1 correspond to here 14, and these are the 14. 1, 2, 3, 4, 5 is the 14. And C1 is the range. Range means your distance. You can see here, this is 23,000 kilometers about. So this is the estimated range from the C by A code. When you see the C2, this observation is not available, C5 not available, but then again you see P is a P code or range, which is again 24,000 kilometers or 23,000 kilometers, 23,000. Now, if you subtract simply with P1 minus P2, these two ranges, which are different, you can see there is a character difference, 648 and 654.3. If you take a difference, you directly get the first hand estimate of the ionospheric TEC in terms of the TEC units. And that is what the beauty of dual frequency measurements. Then there are signal to noise ratio and other things. In the navigation data, you actually do get a kind of information on the satellite orbit, what I said, the Keplerian elements and the clock errors and the orbital elements. So this is again like a formatted data. You can see the manuals and you can read it easily. What we get from this observation file here in the left side is the ranges. In the right side, we can compute the azimuth and elevation of the satellite because the orbit is available. So both are required for ionosphere or atmospheric research. O file and N file. They are called O file, N file. There is one more file called SP3 file, which is, this is the N file is broadcast orbit, I told you, but SP3 file is a precise orbit file, which is coming after 2 or 3 days of the real-time transmission. And they are precise orbit, SP3, they call it precise orbit files. So we can use precise orbit files also. If we use the code, as I told you, like P1 minus P2 or C1 minus P2 or C1 minus P1, that kind of differences on two different frequencies, then we get this kind of noisy TEC values. You can see here. Why it is noisy? Because code measurements are not very precise. Their chip transitions are happening after some distance of like 30 meter or 300 meter, about 300 meter or about 30 meter, with respect to your modulation difference, bit transitions. So every time you have a what you call the noisy measurement, which is fluctuating around that particular errors in terms of TEC or in terms of differential range delay. So TEC is nothing but differential range. So this differential range fluctuate in the code, but when you come to the carrier phase, which is the difference between these two L1, L2 phases, carrier phases, then it becomes very precise, up to millimeter level accuracy. But the issue with phase measurement is the integer number of cycles, which are unknown. The N1 in the first frequency and N2 in the second frequency. When you convert into wavelength, I mean the number, you can multiply with this, so it changes into meters, and you get the TEC in terms of differential of the meters. But then this number becomes very large, and this becomes a relative TEC. So what we do, we smooth these ambiguous phase variations with the absolute code TEC, and we level them, and we get the blue curve, which is the TEC, but still it is coming negative, as you can see, and this is called the bias uncorrected. This is not corrected for the DC bias. What is the DCB bias? Here it is, BR and BS. BR, BS is receiver bias and satellite bias in the electronic devices. They are also frequency dependent, so this is where we have to correct for individual receiver and individual satellite, and then becomes the final TEC measurement. So how they look like final TEC measurement when we see from, like, for example, NavIC observation. I have just plotted for your kind of understanding only some kind of 11 days of data continuously. And as I told you that ionosphere has a day and night variation, which is very, very easily visible here. That during day it goes to a peak of something like 27, 28 TEC, 30 TEC units in vertical TEC terms, and it comes down to almost like 2 TEC, 1 TEC unit in the night, which is almost like post midnight, around 2 o'clock, 3 o'clock, 4 o'clock in the night. It is minimum in the ionosphere. Then again, with the first light of the sunrise, it starts picking up. It rises very fast up to 10 o'clock, and it acquires again a stable TEC for a given place, almost like same afternoon, around 2 to 3 o'clock, and it comes down again. So this is a diurnal variation. Every day it happens, and it happens invariably for all the days. Now, what is interesting here is these are 3 different satellites, 3, 6, and 7, in different color. Now 3, 6, and 7, I just want to go back and connect you with the NavIC positions. This is why the information of the satellite is important. You see 3 was here. This is 3, just overhead our India, 83 degree east. 6 is in the western location of around 34 degree, and 7 is in eastern location from India, 131 degree. So the difference of these longitudes, actually this is at 36,000 kilometer, but when we come to the atmospheric altitude of 350 kilometer, this difference comes to be around 3 degree. So the TEC which I have shown here from 3 different satellites which are geostationary, they are continuously showing the TEC variations which are very different. This is like within 600 to 700 kilometer in east-west direction over the Gadanki, which is around 13 degree latitude. The differences are very large. You can see that one satellite is showing around 15, 17 TEC, and another satellite at the same time is showing around this. So this is called the local time difference. Local time means your sun is also traversing, so solar terminator is traversing, so you have different conditions at different places in terms of the longitudes, so different longitude behave differently. Again, further complexity arises when you have multiple peaks during a day. You can see there is a hump structure, like decreasing during daytime, again increasing. Then there are further other differences which go more than 11 days. Like every day there is a different kind of peak happening at different places. Like sometimes the red color is higher than the green color, and sometimes the blue color is higher than the green color. So you have those day-to-day variability at particular space or particular longitude. And these are the longitude of the ionospheric Pierce point when I talked about, and these are the locations of the satellite. So this comes around 3 to 4 degree, and between the blue color, I mean the red color and green color, there is a difference of around 8 degree. 8 degree means around 800 kilometers. So maximum difference. Now, if I go to the GPS, then this is the situation. Situation is simple, that if I plot all the GPS satellite TEC slanted delay in meters, or TEC unit also we can convert. And these red curves actually individual satellite, because satellite is moving and multiple satellites are visible, so we have multiple TEC curves for a given time of IST. So for that moment, if you see around 2 o'clock, then you see multiple TEC variations which are at as low as around 8 TEC and as high as 40 TEC for the same time from different directions. So this is also an important issue, that when you are using a constellation of satellite, then there is a horizontal difference between TEC from different directions. So how to actually model these and give a proper correction to the user which is receiving a particular satellite signal from a particular direction, so that he will correct it and so that the position will be much better. So this is the challenge in terms of when it comes to the equatorial ionization anomaly or the low latitude, which I already told you in the beginning. When we are observing here, what we see here, that this peak, which is the peak of all the TC during the daytime for a given time, this blue curve actually changes drastically when it is solar maximum condition and then when it is solar minimum. You see how TEC becomes as low as 12 TEC. The peak TEC becomes very low during low solar like 2009 and high solar like 2015 or 14. 14 was the solar peak of the last solar cycle. Now we are going towards the next solar cycle 25. So again in 2020 the situation was like red color, 2019-20, and in 24-25 the situation. But then since solar cycles are so different, again the TEC will be so different. So unpredictability at the solar cycle level is also very large. This is a simple, like I wanted to say that how seasons are behaving, different months are behaving. When ionospheric delay comes into picture, then this is the low solar activity and the high solar activity. You can see the difference of 3 times. Here I showed you already. Here it is the difference of 3 or 4 times. This is directly coming with respect to season wise and day wise also. Each day to day and this. So it's a maximum 35, here maximum around 100. And you see equinoxes show the largest TC or the largest delay when compared to the solstice. Solstice means summer or winter. And there also there is a large variability from one day to another day. And then there is a start and end of the peak density or the peak electron TC. So these variations are almost like right now not possible by any ionospheric model, whatever physics based or the operational or the machine learning model. So this is remaining as a challenge to forecast these kind of variations over a site and over a large domain like India. Then situation is not simple. Situation is little more complex. Here I will say that I already told you there is a signal of opportunity, but then ionosphere becomes a major problem. So how to solve that problem is that we study using the signal, using the ionosphere, using the signal and the propagation properties, and then we give a feedback to the mitigation for the system. So if system wants the ionospheric community to give the inputs, then the ionospheric community must be provided with what actually is high resolution observations or very high possibility of correction models and machine learning and those kind of resources. Then actually we can really resolve this problem. I will come to that later on, but then this is a feedback. Now I told you already this one. And what is the another problem? Another problem is the equatorial plasma bubble that is in night time. I have not talked so far about the nighttime problems. This was the daytime issue. All these issues were daytime. These are all like daytime. You can see here, this is my daytime IST. Nighttime, I have told you that this is very low value. But in this low value is a hidden challenge or hidden problem, which is known as equatorial plasma bubble. Means that there are irregularities in the electron density in this particular volume of ionosphere. So when you have the planar wave, which is coming from GPS satellite, they become highly scattering and the reflecting and the scintillating. So you actually receive the signal with lot of intensity variation. Your I and Q of the signal, the under root square I square plus Q square, the signal intensity varies randomly, and that happens over a large space in the Indian region, and that is known as equatorial plasma bubble. Now, equatorial plasma bubble phenomena actually is known as ionospheric irregularity, one of the ionospheric irregularity, which is a challenging problem. And what we receive is a scintillating. So this is how they look like in the east-west versus altitude domain. They are large-scale structures in the ionosphere, and they cause the depletions in TC and scintillations in the intensity of the signal. And so we represent them as ionospheric scintillation or Esper index, and in terms of TEC or delay, we represent them as depletions. This is how they look like in different observing instrument. If you have an air glow in the night air glow system, all sky system, then they appear like this kind of irregularity where the geometric north is in this side and this is the geometric south side. And you see how branching happens for different kind of elongated bubbles, and this east-west distance is something around 500 kilometer and north-south is around 2000 kilometer or 500 to 700 kilometer. So you see large scale depletions in the electron density are actually happening, and when we see the same in radar, they look like vertical bubbles in the radar. So these are the radar echoes from the refractive index fluctuation from Gadanki, and we see them like different kind of bubble phenomena. If you use rocket, then also we see multiple irregularities in the in situ measurements. And when we see the trans-ionospheric signal, we see in this kind of blue. So without this scintillation, this was like fluctuating in a very small noisy way. But when scintillation happen or this kind of irregularity cross the line of sight, then we get these kind of perturbations in the signal which is received. These perturbations result in this kind of loss of log. You see there is no signal continuously for maybe 2 minutes, 3 minutes, 5 minutes, and this happens randomly anytime. You can see here also it is happening. So multiple loss of log happens. When loss of log happens, user don't have any signal, and that actually becomes a major problem at the L-band satellite communication or the transmission. This is how they can actually come in patches, because different irregularity pass over the particular site in different time, and the irregularity is also drift. Then there is a solar cycle variability inbuilt in that, and there is a day-to-day or night-to-night variability inbuilt in that. This is how the scintillation behave around the globe. Again, it is a very, very important phenomena for low latitude like India. You can see here, this slide is taken from another colleague, and where India is shown here, and then you see wherever the low latitude around the globe is there, the scintillation phenomena actually hinder the communication and navigation solutions. How actually it looks like in TEC, if you see, in the left side is the TEC which I have corrected, but if you do not correct, you just plot what is observed in that observation file, it looks like the blue curve. You see how many cycle slips are happening in the phase. These are called the cycle slips. This is TEC, but cycle slip affected TEC. It is not the TEC which is what you directly get from the code. It is the phase TEC, and since phase is having those n number of cycles, and those cycles are changing after every loss of log, so you have a reset of the counter and new cycle is added. So that is called the cycle slip. So your phase counter is changing, and that makes a lot of trouble for estimation of the phase TEC. And there was a large depletion in the TEC which was sitting at the time of after around 8:30 IST, and that was causing this particular large cycle slip and the number of occurrences of the loss of log. And again, there was a smooth transition of TEC because there was nothing. And then, so how it actually translates into the position. So I have taken 2 nights of 31st January and the 21st March of 2014, and one night without the irregularity occurrence, another night with the equatorial plasma bubble occurrence. You can see here in the TEC and the S4 index, and then we compute the position from the kinematic PPP, KPPP kind of solution, and you see that even the best of the available positions techniques are actually showing large fluctuations of around 10 to 15 meters. So which otherwise remains in kind of millimeter level. So this is the pictorial representation of what we are facing in day and night over Indian region. The way the ionospheric delay changes with respect to time and space, and one need to really understand this daytime ionosphere and nighttime ionosphere. This is how global ionosphere looks like at different levels. This is at 350 kilometer level, this is 400 and 450. So the maximum delay comes contributed from the F2 region. I already told you where the electron density is peaking, and there is a longitude difference. You can see here. If you slice ionosphere at different longitude at the same time, you see different kind of variability in the equatorial ionization anomaly zone. And we have also studied the solar cycle variability, like the 11-year average of different seasons and how they look like. So again, a matter of almost like 3 times from high to low solar activity is coming with respect to different seasons. So seasons are also behaving very differently. Then on top of that, with respect to day-to-day, day-night, and irregularity and all, there are space weather effect. Means something which is actually ejected from the sun as a solar plasma. If you see here, there is a kind of a coronal mass ejection and a comparable size of Earth here. In true reference, it is put here, and you can see how much sun can be dangerous for the small size planet like Earth. But what we have, for God's sake, fortunately, one magnetosphere. And once I told you that there is a magnetic field, then plasma has to move along the field line, and actually it saves us from direct bombardment of the solar particle and the solar the harsh coronal mass ejections directly reaching that. But then still we are not free from the effect. The effect come within few minutes, within 1 day, or within 1 to 4 days, in different class of solar emissions. Like when the geometric storms are there, when CMEs are coming, then the whole ionosphere is perturbed for 1 to 4 days, and when radiation storms are there, and when there are solar flares. So I have just plotted for your interest, when solar storm happen in different month. This is the mean VTC for the different month from using the NavIC constellation for one particular satellite. And when solar storm happen, these different colors represent the solar storm variations of the ionosphere. And different months show the different kind of storms which can happen randomly based on the solar perturbations. Some months do not have any other storm, so I'm representing them empty. But you see here how storms can actually change the perturbations in the ionosphere. Coming to the opportunities which are available for the beginners, or for the people who are interested in research of atmosphere or ionospheric community, and for the purpose of geodesy, or for the purpose of precise orbit computation, for the purpose of position and timing corrections, there are globally available receiver data. Means that you have freely available data. Public resources are there from 400 receivers or the in the IGS, and more than around 2,500 receivers from the UNAVECO website. You have to just register and get the data, and you can process that data. Raw data will be available, and then you can actually do the research component, and you can add to the community's knowledge. We also did similar research using these kind of data sets for some kind of space weather storm, and we actually estimated the TEC from 85 stations, and we published result recently. And what we see during a storm here, that TEC shows a drastic perturbation, especially for a given window of around 3 hours. This is like 3 hours window. These plots are ionospheric Pierce point IPP plots, and 3 hours of satellite path I have plotted. You see how it changes from almost like minus 150 TEC units to 40 TEC units when compared to the quiet time. Is a difference VTC. So there are negative storm effect which are known here. During that day of 18 March recovery phase, there is a positive storm effect, and there is a very large spread negative storm effect in the recovery phase all over. So you see how different latitudes and longitudes behave differently during the storm. For the detail, you can read this paper which is now published. Further application of this particular resource, which is the GPS signal in the space, people use for the radio occultation, which actually you put one receiver in the low Earth orbiter satellite, and then signal passes through the ionospheric layers, and you get the reflected signal here, and we can get the vertical profile at the impact point. So vertical profile of the atmospheric temperature, humidity, and vertical profile of electron density at that point is possible. Several missions have flown. Data is available for your particular use, and for the research and the other operational purpose. In fact, the atmospheric temperature and humidity profiles actually are contributing for the large correction in our weather models and the weather forecast. Similarly, the cosmic and Formosat 2 and Formosat 1 data has been used by different researchers to improve the ionospheric forecast model. You can note down these resources which are available globally. They are not only limited up to these 6 resources. This is just a small list which you can start with, and then it will give you a lot of information about the geodetic community. Then there is a SDR, which is like software defined radio, which is freely available resource. You can develop your own receiver, and you can learn a lot of information about the SDR and GNSS signals. Then there are like GNSS pages or the GNSS groups. There are article.lib, which is a large scale library, and CDDIS NASA is a very, very big pool of resource of the data sets and different products of the GPS around the globe. What we can do with this data set is we can meet several challenges, which for the beginners is not possible, but you can start your research. We are also trying our part into it, and we started developing a receiver network now, which is having some 13 to 15 receivers, which are ionospheric scintillation monitoring capacity. There are other receivers in the community with what is called the reference receivers. And nowadays, there are n number of receivers, like maybe hundreds of receivers available in India through the Survey of India organization. Ultimately, what actually we look for when we see the GPS or the NavIC or these kind of resources, so they are actually the opportunity for research, but then they have actually offer us large amount of data and observation, and actually define a data mining resource. And there we can play with algorithm techniques, machine learning, processing data, then several mathematical algorithm for quality check. We can have raw data and conversion techniques. So it's like a complete domain. Then comes a large domain of applications which require the precise positioning or different kind of users of different sets of applications. And these all, if they talk together with each other and cross talk, then actually we can have a kind of a good harmony between science research, data, and applications. And that is what we look forward, or is a way forward, that if we want to do very good research, we require a lot of data. That data actually will be driven by the applications, and then ultimately applications will have feedback from the research. This is all they are essential for economy. That is what you will listen from many speakers. And this is my last slide before I give you an opportunity to ask me anything as a free question, anything which is related to either this slide or anything else. Thank you very much.
Okay, thank you.
You can.
Okay, yeah. Thank you very much, Dr. Dashora, for your very interesting talk. Rather, obviously, how we can use the GNSS signals for ionospheric probing. But the main part, what I felt, what would be useful for the young researchers and also the mature researchers who are present here, that what would be the philosophy? Why we should do this? Why yes. GNSS is important? That's a very interesting part of what you yes. covered. So on behalf of all of us, once again, thank you very much. And now the floor is open for any questions. So what we would like to do, that we want to close up without taking a break. Will that suit you, or we will take a break and come back?
I think we should continue, sir.
Okay.
If there's no technical limitation, we'll continue. And
no technical limitation. So what we do, okay. that you ask any question, whatsoever you like on this presentation or whatsoever coming into your mind. But because once again, this is a very unique opportunity. So keep on asking question, interacting, and obviously a very important part at the end of the lecture and also at the beginning of the lecture, what Dr. Dashora has said, that he's open for any type of interaction, questions, and openly he has given his email. Rarely what we found in our community that we have to wait for some time to get access to a particular researcher. So I would request all the participants, the floor is open for any question. So please.
Anindya sir, here.
Yes, you are clear. Please directly ask the question to Dr. Dashora. Yes, you are audible.
Can you please show the slide for the TEC depletion? And may I ask you, what was the elevation angle you selected for your work?
Okay. Just 1 minute.
Because we selected around minimum 50-degree elevation angles. But I think in one slide, it was greater than or around 40-degree, if I am not that wrong. Yes.
Actually, here the elevation angle cutoff is 25 degree.
25.
But I have one more plot for this. But this is very old diesel of 210. But I have one more plot which actually has elevation angle also with this. This was a published work. So, but then I keep my elevation angle for the site at 25 degree, because it depends on your multipath around the site. So
Yes.
one single value will not work for this. For my site which is very clear, still I keep 25 degree, because I don't want to have multipath effect on the signal.
Sir, do you think that during solar maximum or ascending or this phase also, 25-degree cutoff will be safe? What is your hunch, or what is your?
Safe from what point of view? You please explain. Safe in what sense?
Suppose we want to calculate TC depletion for multiple links, like suppose for GPS or for multi-constellation. So if you want to do some moving average, or want to add some average section, so what would be safe in terms of TC depletion calculation or scintillation monitoring to have a clear cutoff for TC?
Okay. So you can read one paper which I also generally refer. The paper by Ramarao et al. 2007. It is a radio science paper, and there what they have done very simply, they have shown that if you change the elevation angle for the conversion factor from slant to vertical, then what is the error just because of the mathematical transformation can happen, percentage error. So then any user has to decide that how much error he can absorb for his particular application. He can use that particular cutoff. So for the purpose that there is a assumption, I have already told you that this 350 kilometer. Now what they have shown is that if I actually keep this variable like 300, 325, 350, 375, 400, then how the error for a given elevation angle changes, that also they have computed. Very good paper. Both way they have computed.
They have added safety component also.
So there you will find out your answer, that for your application, like what is your application, I'm not aware right now, but you can choose based on what elevation angle you want to have, and what is the limit that you can allow those errors because of the mathematical transformation. Okay. So for the purpose of research, like I'm studying the depletions, I think 30 degree with 350 kilometer has been working, but then it is not accurate, because nothing is accurate, because this is assumption. Isn't correct na?
True. When we worked under Ashish Das Gupta's team, like 2011 to 2014, we used 50 elevation cutoff for 350 IPP height for doing average, all that. That is why I am asking. But still,
for what purpose? No, different purpose have different. That's what I'm telling you. Again, you are changing your purpose, then your elevation cutoff will change. What is the purpose you are talking? Tell me.
Mainly calculation of TC depletion.
Above 50 degree, what happens is, I will tell you in one small sentence. Above 50 degree, here. This you can see na, this diagonal curve. I will show one better way. Wait. Here. So you have now several satellites, and this is about 25 degrees. So visibility is there. You can see. Now, if you limit your visibility above your site up to 50 degree, then what will happen is many satellites will go from your field of view. So you will have a lot of data breaks here. Like you will have one data here, then after some time one data here, then some data here. So like random points will come, because you don't know above 50 degree which satellite is appearing. So if you limit that kind of thing, then you are limiting in temporal domain lot of variability, and you cannot be like really doing the depletion research, because for depletion to continuously monitor, you require at least signals to be coming to you. So for average TC above over a site, like this is what I think I have also read Ashik Pal's paper. They use 50 degree and above if they want to take TC average, so that your inward conversion errors will be smallest, still your average will be better. Okay, not for the depletion analysis. That is for the average TEC analysis, the total delay analysis. That is what I understand.
Yeah.
unclear.
May I ask you another question that
Yeah,
I have not on?
please.
During solar storm, what is the performance of NavIC? I think
Performance of NavIC in what terms you want to know?
scintillation.
So scintillation, when you talk, uh, the NavIC transmits in L5 band and the S band. Okay.
Yes. Yes.
Scintillation is a frequency dependent phenomena again.
Hmm.
So for the lower frequency part, which is starting at around 1.1 gigahertz, the scintillation will be much higher, and higher frequency part, which is 1.6 gigahertz, scintillation will be lesser, and 2.4 gigahertz scintillation will be further lesser. Okay, number one. Number two, one must think that NavIC transmit in L5, and most of the receivers which are commercially available use the L5 signal. So we can compare L5 of NavIC with L5 of GPS. For that purpose, we have published two papers recently. Both are in GPS solution. It is Srinivasu et al. 2018. You must see in Advances in Space Research, and another one is there, which is Srinivasu et al. In GPS solution in 2022. These two papers you must read before you really come to some conclusion how NavIC will perform. NavIC performance is equal to what GPS or at par with any other satellite system. Number third, the part 3 is that performance of any receiver also contribute to the accuracy of the position. Like if you have single frequency receiver, then the performance will be much degraded than if you have the dual frequency receiver. Then in dual frequency class of receivers, there are the hardware receiver and there are the software receiver. If you have software receiver with that kind of tuning, that during the scintillation, it is changing its bandwidth of the PLL and the DLL, and it is able to adjust those fluctuations, then you have less number of loss of log. Then you continually do the signal recording, or the user is having signal, then effects will be less. So performance is a function of the frequency, the satellite, the constellation, and the receiver. So you cannot directly bluntly talk about NavIC performance. NavIC is at par with, because transmission is at par with any other satellite system when it comes to scintillation. Hope I have answered.
Thank you. Thank you so much.
Okay. Anybody else?
Yes, sir. Good evening, sir.
Yeah.
Okay. Sir, when we are taking Rhinex data from any receiver like Java and Leica, we are considering those data which are in between 3 p.m. to next day 8 a.m. or 8:30 a.m. So why we are not taking the data 8:30 a.m. and between 3 p.m.?
Acha, which one? Let me see. My slide you are referring?
Yes, sir. Yes, sir.
Yeah. This one? This one?
Yes.
This is the slide you are referring? Please confirm.
Yes. Yes, sir. Yes, sir. Please.
Where I have written 8 p.m. Tell me.
No, sir. Yeah, I am just working on this data processing. So that are my questions. When are we getting data from any receiver? So in this time between, there is more data we are get. So why is not getting time between 8 a.m. to 3 p.m. that time?
8 a.m. to 3 p.m. you are not getting data. This is your question. Please clarify question, then I can answer. What is your
yes, sir. Yes, sir. Yes, sir.
8 a.m. to 3 p.m. you are not getting NavIC data. This is what you are telling.
Yes, sir.
No. There is some. There must be some misunderstanding. Actually, we have not recorded data during the time. We were interested from late afternoon to next day morning. That's all. We have not collected the data. That's why nothing else. Probably you got some misunderstanding.
No. NavIC is continuously transmitting the data, and your receiver also is continuously receiving if you are operating it properly. So if you are operating continuously, you will get the continuous data set. Doesn't matter too much. And then if you have continuous data set, you can analyze. I am showing here everyday data. You can see continuous data is there from all the satellites.
Yes, sir.
You can get it, no problem. No
Okay,
issues.
sir. Thank you.
Sir, I have one question.
Yeah.
Actually, first of all, I want to thank you for your very interesting talk.
Yeah.
Actually, we are trying to do some work with the ANASCO, that is online site, and downloading some data for TC analyzing purpose. But if we want to do the work with the scintillation data, is the data is reliable from that online sites? Is it work properly? Actually, we have done some work of scintillation from the septentrion data or usual data receivers, which are very much accurate. But can we do work with the work of scintillation from these online sites data?
Okay. So there are like three parts of this question. Listen properly. Number one is that scintillation. When you refer to scintillation, then there are already, I told you, there is a intensity or the power of the signal scintillation, which is called amplitude scintillation, and second is phase scintillation.
Yes.
So the amplitude
Amplitude
scintillation.
scintillation. Yes, I refer to S4, but as amplitude scintillation part.
Which one you are referring to?
S4, that is amplitude scintillation.
So now for the S4 index to compute, or the scintillation parameter to compute, you require the signal intensity to be sampled higher than 25 hertz.
Yes, yes.
Which is not possible from the other resources. They are sampling at 30 seconds. 30 seconds is very, very slow, dead slow for S4. Actually, nothing, you cannot compute.
At least we need 1 hertz or 1 hertz at least.
No. Who told you?
10 hertz, 25 hertz.
From where you are getting 1 hertz information?
No, I am just asking. That is 25 hertz or
listen, I will clarify everything. Now, when you come to amplitude scintillation, you require this, what I have written here, more than 25 for a reliable S4 index at the L band, number one. Now, people talk about still scintillations, which are the phase scintillation using ROTI index. What they do? ROTI index, rate of TC index. I have not shown here. Maybe somewhere I have shown and skipped the slide. This ROTI index, you know, na?
Yes, sir.
Do you know ROTI index? Rate of TC.
That is a phase scintillation part.
So that is that is a kind of phase scintillation, not directly phase scintillation. Here, this is ROTI.
I have written, yes.
Depending directly TEC, you put the TEC here and get the rate of TEC.
Rate of TEC.
Minus the ensemble square and the root, that is called ROTI for 5 minutes. So every 5 minutes from the 30-second sample data of TEC. So you first compute the TEC from available data of 30 seconds, then do the ROTI index. That ROTI index will resemble that there was a irregularity of size of around 10 kilometer scale or higher. Okay. It is not in the 300 meter and 400 meter. There is a scale of irregularity. So ROTI index will represent the fluctuations of kilometer scale irregularity of 10 kilometer and all that. And then S4 index is up to hundreds of meter, like 300 to 400 meter irregularity. So when people tell that I am using Rhinox data and doing ROTI, means they are still representing the scintillations which are at the higher scale length. Okay. So you can do that, but you cannot compare that with S4 index, because S4 index represents a different class of irregularities. You understand that? So when you do the ROTI, the irregularity size, which is like what you call generally in a very common man language, is the horizontal scale length of the size, which is 10 kilometer kind of size, very large scale irregularity, ROTI. But when you do the S4, your Fresnel diffractions from 300 to 400 meter class of irregularity is considered. So for the S4 and Fresnel relation, you require very high sampling rate, which is not available from the freely resources. You have to purchase scintillation receivers. So that is what I told you in the end, where I was telling that we are developing a network of our own here. These are all scintillation monitoring ISMR receiver. They are called the scintillation monitoring. They are either the Novatel class or Septentra, Polar, RX,
Yes, yes.
and all. So these receivers are scintillation monitoring. There you get the S4 index with high rate data. The sigma file, you can get the ROTI, whatever ionospheric parameter you want. Am I clear now?
Okay, thank you, sir.
Yeah. Anybody else?
There are two more questions. One from Supa, the smaller one. I will take it first, and then okay, you take it.
Yeah, Rahul Mandal, na? Yeah, I am reading the question that how observation and navigation files are used to get solutions of different kind of post-processing. Some of the software use only observation files to get PPP solution, but some of them need observation and navigation both. What is the difference of usage of two different files? How one gets solution? Okay. So if Rahul Mandal is online, then if he's listening, I can give answer. Are you online?
Yes, sir. Yes, sir.
Okay. So answer goes like this. Simple. Very simple. Keep it very simple. Here I am showing you the position computation which has a different class altogether. They are called the position solutions. The one which you get using the single frequency receiver is called the standard positioning solution. Anna? Standard positioning, SPS. You understand that? Standard positioning means the accuracy will be not better than 5 meters. Sometimes it can go to 1 meter, but not better than meter. Then comes your precise positioning techniques, where you actually use the phase of the signal, high accurate phase of the signal, and then use the techniques like double difference, like the multiple differences, or you use the what you call the reference and the rover kind of thing. So people call it precise positioning technique, PPP. Okay. Now there are 3 or 4 major software available now freely for PPP. One is the Canadian Space Agency software. You can write it down. Canadian Space Agency software. Second is the RTK-lib. And third is the, which is not free. RTK-lib is also free. Canadian Space Agency online free. And the third one is NASA Gypsy. Okay. Gypsy X. So these 3 software, one more is there. Like there are like 4 or 5 major software. Like Burmese is also there. Gamete is also there. Huh? These are all software. Now, when you come to PPP, precise point positioning class of solution, then you must use SP3 solution. What is that? Navigation file, which is post-process mode. After 3 days only, it will be there. In real time, if you want to do, then there are other techniques. You have to go into research domain and search the GPS solution and this kind of journals. That what are the techniques for real-time PPP. But when we do the real-time...
Sir, actually, my question was in RTK-lib, I saw there are to get PPP solution, it needs observation files and navigation files both. But when I use the GPX software, it's only need observation files. It don't need any navigation files. So my question is how it uses the navigation file in RTK-lib.
You should have asked like this only. You have asked open general questions or general answer. Now, particular question RTK-lib. RTK-lib is a downloadable software. There you have to give the observation file and navigation file. Now, the RTK-lib uses navigation file, but then can you tell me which PPP you are using, static or kinematic?
Sir, it's a kinematic.
That kinematic you cannot do with this navigation file. There will be error in the RTK-lib also. You cannot run that with the navigation file. It has to be provided with SP3 file. You can select that SP3. Then otherwise you have to give a very precise position of your receiver. If you are not having the positioning, so it will compute with respect to that position. Number 1.
Okay,
Number 2, Gypsy actually downloads in real time. It actually, if internet is not there, Gypsy will not work. It's an online software, and even if they give license, it has to be online only. In offline mode, you have to give SP3 file. In online mode, it automatically downloads the SP3 file and compute. It will not ask you anything else. Since SP3 files are available globally, freely available, they download themselves. They don't have to ask you. Because from observation file, they get the day of the observation and the epoch of the observation, corresponding file they download and they give it. So, but then for PPP, SP3 is must. Okay.
Okay, sir.
Fine.
Okay, thank you, sir.
Yes. Anything else? Then one more question by Sukabya is there. That according to you, what will be safe elevation cutoff for scintillation study? Then when you call safe, I feel danger because there is nothing safe. Okay, so for scintillation, elevation cutoff is directly dependent on multipath, your site multipath. If you have a very clear site, very high antenna with your almost like 5-degree elevation angle, there is nothing visible, your horizon clear, you can go up to 5-degree elevation cutoff because multipath contribution will not be there. But as soon as you are in a urban environment, in an environment where hills, trees, or any building, construction, mobile tower, something is there, you cannot keep a same elevation cutoff like 30-degree all around. You have to compute a multipath map. Remember, without multipath map, no standard scintillation study is made. You go to any JGR, my own paper, or anybody else's paper, they actually consider multipath rejection criteria first. What is your multipath rejection? You have to decide whether I am receiving a multipath pattern or a scintillation pattern because of ionosphere. Then that comes from the multipath map of a site. Then you decide that, okay, I have the ionospheric information now. Now I can process this for the scintillation studies. So this is the answer. You have to have multipath rejection or multipath removal criteria for a given site. Nothing is safe.
Okay, sir. Sir, another question. Sir, what is the basic difference between the special purpose scintillation receivers and the commercial geodetic receivers?
Only one difference. These receivers, which are, I told you some photos here. These are like mostly I have put here the Septentrio and the Novatel. They are called the scintillation monitoring receivers, and the Trimble and Javad, they are called the reference receivers. Now, in the scintillation receivers of this kind, they actually define the wide bandwidth of the PLL and DLL, little wider. Then they have automatic gain control also. So this AGC actually will be turned off during the scintillation recording. Otherwise, in the reference receiver, you will have AGC, which will actually control the gain when the fluctuations are happening, so that they want to avoid the fluctuation, remember. And the scintillation receiver want to capture those fluctuations. So this is the basic difference. So they filter out, try to filter out those fluctuations which are in phase or intensity, and these receivers try to get those more and more. So they actually receive a lot of noise also, and because of the high bandwidth, they receive what you call lesser accuracy in the code and phase measurements. Here in these reference receivers, because they have a lot of filters working, they have very precise phase measurements and very precise intensity measurement. But the trouble is that as soon as scintillation happens, the reference receiver lose log very fast because filters will fail, their bandwidths will fail. So lot of loss of log event will happen in reference receiver, but less loss of log will happen in the in this kind of receiver. The second difference is that scintillation monitoring receivers compute the indices which are called the S4 index and the sigma phi index inside the receiver at the chip level, and they provide ISMR data. ISMR means ionospheric scintillation monitoring record, that kind of data for each satellite for each minute. But reference receiver do not provide that. Reference receiver provide only Rhinox data at every 30 seconds or whatever 1 hertz or whatever 25 hertz. They provide the Rhinox data. But these receivers provide the scintillation index directly available, S4 and sigma phi, and other information for each satellite. That's why they are the ISMR receivers. Am I clear?
Yes, sir. So, can we study scintillation using those reference receivers?
That is what I told to previous, I think, Arpita Guha boss, that you can use. I think you were sleeping at that time, Sukabo.
No, sir. Actually, we can log at a rate of 50 hertz data using this receiver, reference receiver.
Data, but what data you will get?
What data means, sir?
You will get this C by N node data from these reference receivers at 50 hertz. Okay. Now,
Yes, sir.
then in that case, you have to compute S4 index for yourself.
Yes, sir.
Correct. Once you compute S4 index, you will find that C by N naught is not the quantity which goes in the S4 computation. S4 computation requires intensity.
Yes, sir.
Not the C by N naught. So then you have to convert into intensity using one model. What is that mathematical transformation?
Yes,
Then
sir.
you find out that your S4 index is not matching. Then you will complain. Here, you see, the signal power is not the C by N naught here. Okay. So it will be S4 index, which is called the equivalent S4 index from the C by N naught, that kind of thing. Okay. But you can do it, but it requires a special class of observations like reference receiver. If you run at 50 hertz, it generate, I think, maybe 1 GB data per 10 minutes, something like that, or per minute 2-3 GB data, something like that.
Yes, yes, yes.
So then you have to sit there and do, or you have to have very intelligent software which can actually retrieve the data and then do the job for you. But then processing becomes another major difficulty. So people don't use reference receiver for the purpose of scintillation study. They can use it for ROTI kind of study, ROTI, rate of TEC index, but not
Okay.
for S4 or the sigma phi.
Okay. Okay, sir. Thank you. I got my answer.
Yeah. I think there are no other questions, sir. Anindya, Professor Anindya Bose.
Yes. So I cannot see any more questions, but still the floor is open. Anybody can ask question.
Yeah, I'm
Sir,
available.
Sir, I
Tell me.
I have another question that when you talk about the EPB, then you talk about that sometimes we get no data, that is loss of log condition. Sir, I want to know that that time is total internal reflection is occurred in the ionosphere region, or there is any chance for the signal from the ionosphere to suffer from the total internal reflection and get back to the space again, and we get no data.
Okay. So it is partly your question is related with the radio wave propagation. That is what I referred here. That when you are talking about total internal reflection, actually you are not getting the concept of how the theory of radio wave propagation through the ionosphere happens. So please read these 3 books. I will give you a basic answer that total internal reflection in the ionosphere has a different kind of theory, because you have magnetoionic theory. The magnetic field comes into picture, so it depends on the not only the electron density but the angle of the ray path with the magnetic field line when it is crossing the magnetic field line. So that's why this complex quantity and refractive index variation comes, but then total internal reflection is not there, number 1. Number 2, that what are other effects which are happening if not the total internal reflection? So the other effects are the refractive index variation, then there is a absorption, then there is a what you call phase advance, group delay, then there is a scintillation, then there is a scattering, then there is a diffraction. These are the effects which are happening when the radio wave travels through the ionosphere. Now, the most important 3 effects are absorption, scattering, and the scintillation. These 3 effects and the diffraction, 4th one, these 4 effects can simultaneously happen or can happen individually at some particular time through when the ionospheric irregularities are happening. So either of these 4 have the capacity to either fully absorb the signal, fully scintillate the signal such that the loss of log occurs in the receiver because of the PLL and DLL bandwidth limitation, or the diffraction happens so strongly that it is called the lensing. Lensing means that the complete signal is, the ionospheric depletion is behaving like a lens. So it is like oversaturation. So that kind of conditions also happen in the ionosphere, and because of that loss of log. So loss of log is a function of the ionospheric refraction, diffraction, absorption, scattering, partly scattering, and also the function of receiver, PLL and DLL log loop, the hardware of the receiver. These are the functions. So loss of log is not directly like you can tell always that it is because of my what you call the ionosphere. Again, I'm telling you, receiver is the antenna is also there, and the receiver electronics. Within the antenna, you have the gain, which is varying from zenith to the azimuth. So at the azimuth, actually the lower gain will be there. They will normalize the gain using the microstrip patch antenna. Then again, another hardware issues are there. And when you have a higher elevation angle, the gain will be better. So signal will be much better. So loss of log can occur because of several these functions. Is not directly related with. Now, what we did is that whenever loss of log has occurred, we find out what is the S4 index. Okay. Then we find there is a very interesting story. And I must ask you to immediately read one paper which is published in 2022 by me. It is Srinivasu et al. In GPS solutions. Srinivasu and Dashora, sorry. For your purpose, I can play it here so that anybody can note it. You can see this, na? Google. Are you able to see my Google?
Sir. Yes, sir.
You type Nirvikar Dashora, go to Google Scholar, and then go to year-wise latest publication. And this one is the one which I am referring. This Srinivasu, this one. Loss of log of GNSS signal, especially the atmospheric reality observed over Indian low latitude. This you download and read it. That will answer all your questions.
Okay, sir. Sir, I don't know about the GNSS system at all. First of all, sir, I am a student of MTech for the Burdwan University, and our respected AB sir give us the opportunity to interact the first time for such the huge program. So, sir, I have much not known the fact. So I have first listening to the all. Then you can say, and I have some, sir, this type of question. Sir, I have, sir.
No, any level of question I always welcome. No issues.
Yes, sir. Yes, sir.
Yeah.
Yes, sir. Sir, that is why, sir, I asking you, sir.
No issues. You must understand. If you are really interested, you go forward and study more.
Okay, sir. Okay, sir.
Fine.
Sir, I have, sir, another question, sir. From the first day, sir, we have some outstanding speakers, sir, as you, and sir, that they, sir, they have told their slide that we can measure the actual pseudo code measurement, or sir, carrier phase measurement. Sir, in pseudo code measurement and in carrier phase measurement, we have the ionospheric error have the different sign. Sir,
Yeah.
I want to know that in your lecture you said that the error for the ionosphere that is occurred, sir, it is due to the phase velocity and group velocity have the different sign. You have
I understood your
told
question. You just see here. I already told, but I think you were sleeping at that time. Listen here. That this is the one which is noisy is at the pseudo range measurement. I have written here code. Code is nothing but pseudo range measurement, and this is how the ionospheric error looks like. This blue curve, noisy curve here, and when you use the phase carrier phase and get the ionosphere, this looks like this smooth. So there are two different kind of ionospheric delays, and then we combine them through some technique of Kalman filter or whatsoever, and then we get the final ionospheric smooth TEC variation. So these are the two things to your answer.
Sir, thank you, sir.
Yeah.
Okay. So if there is no more questions, we will thank once again on behalf of the organization, mostly on behalf of the participants, to Dr. Dashora again. Thank you very much for taking for giving them the opportunity of hearing you, and most importantly, giving access to you for their questions. So thank you once again, and we will hope that if we get some opportunity next year or next year till I retire, so I'll be getting the support from you, so that starting from the scratch level, the experts have the opportunity of hearing you. Thank you very much. Thank you very much.
Thank you, sir, Professor Anindya. And I find in you a very good colleague and a very good expert of GPS. And because of your expertise, you could understand the level I generally present. And I really appreciate your effort in educating different masses and also popularizing the technology of low-cost receivers. And even after retirement, I will be available. Don't worry.
No, till I retire.
Yeah, after your retirement,
till I retire, I'll be doing this type of courses. After that, there will be no chance. So that I told that till I retire.
But sir, we will not leave you. We will use your expertise if we do the workshops.
Okay. Thank you very much. So thank you very much. Second to all the participants and to the expert. Till we meet again tomorrow. So the announcement is tomorrow. The lecture will start at 5:30 because Dr. Dinesh Manandhar would be joining from Tokyo. So their timing is just like the previous case from for Dr. Ivan. So Dr. Dinesh Manandhar will be joining at 5:30. So I would request everybody to be present at 5:25. And tomorrow would be the last day of the online course. So till we meet again, good night and over. Thank you very much. Thank you very much, Nirvikar.
Yeah, good night, sir. Good night to all the participants.
Okay. Okay, good night.
Thank you, sir. Good night.
Thank you. Good night.